Hello, everyone. Today I hold what I hope will be an exciting tutorial on mass balances and flow sheeting. You'll hear from my voice, it's not doing so well. I'm a bit fluid. Started off as a huge sinus attack, and now it's just attacking my voice. But anyways, where there is a will, there is a way. And more importantly, something that I feel is a life lesson that everyone should always keep in mind is always have a why. It makes it easier to do things because once you have a why, the how becomes super easy. So that being said, let's start off with our little mass balance presentation that I've prepared for you. I'm going to run through this quite quickly, but it's something that once you've acquired this particular PDF that I've prepared for you, should you want to go through it yourself, you can always comment on the comment section below with your email address, or just simply send me an email to lungile@sakanteni.co.za, and I will definitely send it to you along with this video. But then this video will be available on YouTube, so there would be no point in looking for it. But then also, I will, at the bottom of this PDF presentation, put in the link to my blog post where you'll be able to go get this particular PDF directly from. So I'm going to run through it quite quickly, but I am available for one-on-one tutoring and more detailed attention to what we're doing here. So mass balances. Again, as I said, it's important to know your why. Then the how becomes easy. So why do mass balances, right? Excuse me for a second. So mass balances, in effect, form a huge part of plant design. They form the basis for calculation for many things. For example, as listed here, you've got energy balances, pipe sizing, valve sizing, equipment sizing, material of construction selection across various sections, utility requirements, CAPEX and OPEX. So considering that most students I get to either are either rusty or very unconfident, sorry if that's not a word, with material balances, I thought it best to go back to the basics. So the plant design lecturer barely has time to go through some of the basics that I'm going to be showing you today. And in most cases, students attempt to solve their plant design projects without going into or without revising the small little details that will help you go through the simulation quicker. Again, with the simulation, I said in our previous blog post, in our previous presentation, you can guess the input. No one is stopping you from doing that. However, by guessing the inputs, you are not designing your process optimally. You are not designing it for what it needs. You are just designing it according to the materials that should be fed into it, and then hoping for a result. Whereas doing a proper mass balance around it is doing proper literature surveillance of getting the correct conversion rate, the correct selectivity rates, getting all that information allows you to set up your mass balance properly, and in this way, setting up your simulation to be as close an approximation to what you want to achieve, right? So that's the reason why I want us to do this. So if you're a student and you're still struggling a bit with basic mass balances, do not be ashamed. This is something that I've had with a lot of students. It's nothing to be ashamed of. Please do ask for help. I am here to help. The two partners that I told you, two partners that are coming on board who are also excited to lend a helping hand. So do not shy away. Your future depends on you stepping out, knowing what you don't know, and not being ashamed to ask for help. I will introduce the two partners that are considering joining me on these video series and blog posts. And yes, let's get started. So, first things first, non-reactive mass balances, right? So, non-reactive mass balances, this is where a typical example would be, for example, a mixer, where you've got stream one, stream two, you put them through a mixer, there is an agitator, and the result is unreacted combination of the two streams. So there is no reaction, right? So I've chosen a simple example where you've got water and salty water, right? Where your water stream is 100 kg per second. It's got a composition of water, which I've denoted as X1H2O is equal to 1. And then, sorry, this was meant to be X1 NaCl is equal to 0. And then stream 2 is M2 equals to 80 kg per second, where again this is supposed to be X2 H2O is equals to 0.5. I'll just remember to fix these. Let me highlight them now so that I do not forget. Again, this is supposed to be X1, and then X2 NaCl is equals to 0.5. So that's your salty water, that's your pure water. And then they are put into a mixer, agitation, nothing much happens, nothing reactive happens in your agitation there, and you get M3. Now, the idea is, the problem statement is specify stream 3 completely, right? So the overall material balance would be M1, M being the mass and 1 denoting stream 1, plus M2 is equals to M3, right? Therefore, M3 is simply the sum of M1 plus M2 on a mass basis, which will give you the total mass of stream 3 is 180 kg per second. Then you come down to the component mass balances. First, you start with the water material balance. Now, it is important to properly define your notations, right? For example, I said M stands for the mass, and then subscript 1 means stream 1, right? X stands for composition, subscript is stream 1, and then H2O. So X1 H2O is the composition of water in stream 1, right? Plus M2 multiplied by the composition of water in stream 2 is equals to M3 multiplied by the composition of water in stream 3. Then you also do a salt balance, which is the same thing. M1, which is stream 1, multiplied by the composition of salt in stream 1, again, plus M2 multiplied by the composition of salt in stream 2 is equals to M3 multiplied by the composition of salt in stream 3, right? And then, as you can see from equation 2, I actually meant to say equation 1 here. It's funny, you should always review your work, because you end up going into a presentation and you start realizing that there's so many mistakes. So what you'll then get is that if you use equation 1, the water balance, then 100 kg per second times 1. Where does the 1 come from? Let's go back to our initial drawing there. You'll see that your composition of water in stream 1 is 1. It's unity. So that's multiplied by 1 plus 80 kg times 0.5, which is your total the total mass of stream 2 is 80 kg per second, and then you multiply by the water content, which is 0.5, right? Is equals to 180 kg per second, and then times the composition of water in stream 3. This means that the composition of water in stream 3 is what? 0.77 by mass. Next, the sum of mass fractions of components in a stream add up to unity. Therefore, we do not have to use equation 3. You can use equation 3. So in order to calculate the composition of salt in stream 3, you'd go through the same process. You substitute the values which you have now. For example, here you've got M1, you've got X1, you've got M2, you've got X2, and you've got M3. You will be able to calculate X3 NaCl. All right? So, but then you can just simply do the composition of salt in stream 3 will be 1 minus the composition of salt of water in stream 3, which is 0.22. Now, what I want you to do is I want you to go through this example carefully, and then to show your understanding, I need you to calculate the mass flow rate of water and the mass flow rate of salt in stream 3, right? So these are the two things I need you to calculate. Should you have any challenges with this, I am here to assist. Drop a comment below or drop me an email and let's try and go through it together. And then to summarize, three of the reasons why material balances are important are revealed in the above example. And probably all of them are revealed in the above example. For example, OPEX and CAPEX, it is revealed there. The size of your vessel will add to the cost. We will add to the equipment cost. That is the capital expenditure. And then your operating expenditure is sometimes calculated as a fraction of the capital expenditure. But then just the simple thinking, if you have a vessel like this, a mixer, chances are if you're doing something like salt, because salt is solid, right? There'll be someone who'll be holding a bucket and adding salt in there. So you can literally, if you're doing an isolated case of this particular system, you can literally say that that guy who is required to pour salt into there will cost me on an operational level 2,000 Rand a day or 2,000 Rand a month or 3,000 Rand a month. So, but then the things that I wanted to look at now were your pipe sizing, where the stream 3, sorry, that was supposed to be stream 3 there. Let me highlight that as well so that I can fix these little things for you in the final document. It's a combination of stream 1 and stream 2. What does that mean? It means that stream 3 is bigger than the two of them combined. If it's bigger, if you want to maintain the same pressure, for example, if inlet 1 and inlet 2 have the same pressure and you want to maintain the same pressure going out, that means your pipe will have to be bigger. So your material balance here is able to show you how big your flow rate is so that you are able to calculate the pipe size that you require. Then there's material of construction. So pipe 1 only has water. Water is not as abrasive as salt. And then pipe 3 is a combination of both, right? So the most abrasive in this case would be what? Solution would be pipe 2 because it has 50% salt, right? Whereas pipe 1 doesn't have that much salt. And then pipe 3 has only 22% salt, right? So it will be less abrasive. So the design engineer will probably design pipe 2 and pipe 3 as the same because the difference is not that much. Obviously, your material guys will tell you that, look, if your salt content is above this percentage, then you definitely need to use this kind of piping. But in most cases, for such differences, it will probably be the same pipe. So you might find that the pipe coming in with water is different to the pipe coming in with the salty water and coming out. So this is an example of how your material of construction can be determined, or a preliminary guess can come from just your mass balance by knowing exactly how much of each component is in each pipe. That will help the design engineer in selecting the right material of construction. And equipment sizing. So the total flow rate coming out of the mixer will help us size the mixer in accordance to residence time in the mixer. So you as the design engineer will say, all right, this vessel should be this big, and because the downstream processes require this and that, I will design this tank, this mixing tank as a hold-up tank, right? So the size of it will depend on how long I want to hold my liquid mixture for before it is sent down line, right? So the mixer can also be used as a temporary storage, as I said, or to even create positive head pressure. So the vessel itself, you put it at a certain height. Once you have water inside it, the water mixture, that creates a pressure, right? If you go back to your, what do they call that equation? The fluid flow equation where there is rho G flow, something like that. But then your positive head, your positive pressure head, will then give you less of a need to have a pump in the stream to send water to send the mixture to the next vessel, right? And then the small challenge that I did for you is what we had done here was we did mixing. So as an example, I'd like you to do evaporation, where now you take the product from the mixer and run it through an evaporator. What do I mean when I say take the product from the mixer? I'm saying take this stream that is defined now, where you've got 180 kgs in total, and its composition is 0.77 water and 0.22 salt. I need you to take the stream, right? Use it, run it to an evaporator. The overhead product, which is the vapor stream, will have 80% water by mass, and then the bottom product has a total flow rate of 30 kg per second. I'd like you to do the following. Draw the process flow diagram for the system, perform the overall material balance, perform the water balance, and then report the following for stream 2 and 3. Salt and water mass fractions, that's the first thing I want. So what I want you to report is what I did here. The salt fraction, the water fraction is there, and the salt fraction is there. I also want to do the same. I want you to do the same thing for all streams. So that will be stream 2 and stream 3, and then also report the salt and water flow rates. This is the same question that I had posed to you here, right? The salt and water flow rates, and you'll be good to go. Now, before starting any calculation, make sure that you give thought to your notations. I meant notations here. So what I mean by that is the way you're going to represent each kind of variable. For example, here, this variable, the composition of water variable, I represented as X3 H2O. So give thought to this, as it allows you down the line in the calculation not to get confused. Because now you can go back, you know that every time I'm saying X3 H2O, I'm talking about the composition of water in stream 3, right? So we've covered non-reactive mass balances. As I said, go through the evaporator example, and then should you have any challenges, please do feel free to come back and check with me. Now, reactive mass balance. Now, I chose the popular Haber process in your first year, the first thing you hear about. I think in high school, you know about it. This is a very popular reaction, quite easy to remember. 3 hydrogens plus 1 nitrogen goes to 2 ammonias, right? So in our example, there's our little process flow diagram. We've got 50 kgs per second of a stream that is 90% hydrogen by mass and 10% of an inert. It's coming in at 25 degrees Celsius, and it's at 2 bar. These are all the things you would need to set up this simulation in a simulator, right? And then down here you've got stream 2, which is 80 kgs per second. It's got nitrogen, 90% by mass, and the same inert as in the first case. It's got 10% of that inert. It's 25 degrees Celsius, and it's at 2 bar. Now, the first thing you need to remember is that reactive mass balance uses moles, not mass. Do not ever make this mistake ever again. Whenever you're doing a reactive mass balance, convert all your incoming streams to mass. But then, obviously, there's going to be something about that in that we're going to discuss just now. And then, to make this example interesting, I have introduced an inert in each stream. And then calculate the number of moles in each stream of nitrogen and hydrogen. So to do that, you first calculate how much hydrogen you actually have in stream 1. And in order to do that, M1H2, that is the hydrogen in stream 1, is equals to M1 multiplied by the composition of hydrogen in stream 1, which will then be equals to 50 kg per second multiplied by 0.9, which will give me 45 kg per second. Then your N1, your moles of hydrogen in stream 1 will be equals to your mass of hydrogen in stream 1 divided by the molecular weight of hydrogen, which will then give you 22.231 kilomoles per second. Similarly, you can calculate N2 number of moles of nitrogen in stream 2. Because of this whole N2 thing, I've denoted your stream 2 with a little asterisk on top, and then this will give you 2.571 kilomoles per second. And then before we proceed, you should you be worried about the inert? This is a question that anyone, I'm sure, should ask themselves, because already I told you that everything should be converted into moles. What about the inert? Well, the answer is no. Because the inert is not reactive, nothing will happen to it in the reactor. Therefore, it will just pass through, so the exact amount that comes in will come out. So for our example, we don't even need to know what the inlet is. We don't even need to know its number of moles, nothing. You don't have to worry about it because it will not change. Its amount, its mass will not change throughout the process. Now, given a composition of 90%, a conversion of 90% of the nitrogen, complete the material balance, right? So this is the equation for conversion. I gave this in the previous lecture, where your nitrogen in stream 2 minus the nitrogen in stream 3 over the nitrogen in stream 2 gives you the conversion. Now, this will give you a nitrogen in stream 3 of 0.2571 kilomoles per second. Now, the number of moles that reacts of nitrogen are directly converted to ammonia. And the way you calculate the number of moles that reacts of nitrogen is you say number of moles of nitrogen that came in, or in this particular case, in stream 1, in stream 2, minus the number of moles that come out, in this particular case is N3, will give you the number of moles that reacts of nitrogen, which will be 2.3139 kilomoles per second. And then from your stoichiometry, we know that N reacts hydrogen over 3. Go back to your stoichiometric reaction there. Let's just take a quick peek at it again. 3N2, 1 nitrogen gives you 2 ammonias. From that, we then come back and say that N reacts nitrogen over 3 is equal to N reacts nitrogen over 1, which is equal to N produced nitrogen over 2, right? And then what this will then give us is, it will then bring us to N reacts hydrogen is equal to 3 times, right, the N reacts of nitrogen. So to calculate the hydrogen, so it's that, right? You then take this 3, you put it over the basic mathematics, and you've got 6.94 kilomoles per second. Similarly, the N produced ammonia will be 4.628 kilomoles per second, right? Now, let's tally up what reports to stream 3. So first things first, the amount of hydrogen that's left and which is going to report to stream 3 will be N1H2 minus N reacts H2, which will be 15.381, right? Therefore, now that we have everything, so N3, we've got it, it's 15.381. N produced, which is equal to N3, NH3, is 4.628. And we had previously calculated our N3 nitrogen. Our N3 nitrogen, where was it? Our N3 nitrogen is 0.257. We can now tally everything up and report it by mass. So that's what we're trying to do here. So then we have M3 hydrogen will be the number of moles of hydrogen multiplied by the molecular weight, which will give us 51.008 kg per second. Then the M3 ammonia will be the number of moles of ammonia multiplied by its molecular weight will be 78.819. And then finally, the number of moles of nitrogen will be 0.257 kilomoles by 28, right, which will be 7.118198 kg per second. So where is the inert? Well, that's a little challenge that I've got for you. So whether it's reactive or not, unless there is accumulation within the reactor, right, the amount by mass that comes into the system must be equal to the amount of mass that comes out from the system. This is not a nuclear reactor. Nothing disappears within the reactor. You're just converting one product to another, one reactant to another form of product. So I'd like you to go in and tally up everything. So add up the masses that you have, and then check that if you add the total inert that came in, right, the stream coming in will be equal to the stream coming out. You do that and you'll be well on your way to understanding mass balances. All right, I hope this was interesting for you. I'd like to cut this video here so that we don't have too long videos are not too long and people get sleepy. And The next video that I'll be uploading right directly after this will be a simulation that I did for a more complex reactive mass balance. And the reason why I chose this is it allows us to look at your feed preparation. It allows us to look at the preliminary mass balance that you do before you do the simulation. And I also did it in such a way that we could have a simple absorber at the back end of the process. So I hope this video series are exciting. And as I said, I hope to know more of you better. And yeah, let's do this. So we're going to end this one here and start with the complex reactive example on the simulator.